I got all this for an Inductors. That's another hour, it looks like. I thought it was going to be maybe an hour, and I was lying. So you guys want to keep going, or do you want me to just hurry the hell up, or what?
I'm good. You can keep going.
I'd like to be done by 9. I have to be up early.
We're not going to be done in 7 minutes.
Well, I can cut out early then.
You
can keep going for them.
We'll see how far I can get. I'll try to speed it up. So there's inductors are as current flows through. There's 2 right-hand rules. As current flows through a wire, electrons flow this way. The magnetic field around it circles this way. So a single wire has self-inductance. I've only ever found one paper from like 1908, the Navy, where somebody's actually done the math to figure this out. I had to go back and find it and reference it to do something else one time. And then I've heard my name. I've heard a paper was done that does this and it computes how to do that. And the people who are talking about it were the people from the customer who were on that program. So I'm thinking, I think I wrote that analysis. And it referenced that paper from 1900 whenever. So there is as the current goes through, the magnetic field expands, and as the current slows down, it contracts. But as it expands, there's a self-inductance on the wire that tries to keep it, because you go the other right-hand rule and you say, oh, if I've got a magnetic field in this direction and an electron moving that way that has a force this way, that's the other right-hand rule. So the magnetic field's going into the wall. That's what, well, coming out of the wall. So these are arrowheads coming out of the wall. If they were going in, they'd be X's, and they'd look like the fletchings on an arrow. Really, I'm not kidding. Boobs are coming out. X's are going in. Sorry, had to go there. It's the convention. So the right-hand rule here, I did that wrong, clearly. Should be going that way. The right-hand rule, field coming out, electron moving this way, there's a force impinge that way. We talked about electric motors one day. That's how an electric motor works. You get a permanent magnet, you're putting a current through it, it's causing the winding to spin. An electron moves through a wire, creates current, creates a magnetic field. Another wire over here nearby, that magnetic field crosses that wire, which causes a reverse current, which tries to make the electron go the opposite direction. This is why you see twisted pairs. Because you're trying to cut down noise and you're trying to cut down outside interference. This electron wants to go that way around. It's a twisted thing, so you got this nice coupled inductance. This one goes that way. It tries to pull an electron that way. It has a tendency to balance the load in the 2 wires. So now when I've got something that sends a signal down that, I create a magnetic field. It pulls an electron this way, which creates a reverse magnetic field, and it nulls. It nulls. If I have outside signal comes in and hits the one, it causes the electron to go this way, but that causes another one to do this way, and it causes it to null the field.
What's the shielding for again? Because you have shielded and unshielded?
So a twisted pair is going to give you, I think, like 3 dB of noise suppression, 3 decibels, so half power. A good shield can give you up to, I think, up to 6 dB of noise suppression, or noise immunity. I've worked with triple shielded type stuff where you have a shield and then a twisted shielded or something like that. And you're
so your standard high high-end coax these days is quad shielded because they're trying to push so much bandwidth through it. Your cable TV stuff that you use in your house is quad shielded.
What they're getting there is...
Well, of course they're not twisted, so I guess they need that.
It's just a coax.
Yeah.
And it's... They're using a foil and a braid, and then maybe another... They're probably doing a foil, a braid, a foil, a braid. Braids are good at high frequencies. Foils are a little bit better at lower frequencies, but they're really not all that good because it's a tape that wraps around. So each has its strong points, and it's the mesh makes a Faraday cage, but the little pinholes in it are leakage points for really high frequencies.
So the foil's supposed to help.
So the foil's supposed to help fill in those gaps, but a foil's not that good because it lets low frequencies in through this big long spiral that goes around it. Because that is a huge hole that goes around, but it's overlapped, so all the high frequencies kind of hit. So if you set that on top of the mesh, they ground together, and it makes a more solid cage. And so you play some games there, and quadruple shielded is... I've seen the math. I can't do the math myself, but I've seen it, and somebody's explained it to me and walked me through it. And once you get past 3, you've really gone as far.
Diminishing returns.
Yeah, you're not getting all that far. The thing is with cable TVs, though, on that, they're running so many signals on there. They're narrow. They're really sharpening the bandwidth. So you've got a signal at 300 megahertz and another one at 310 megahertz and another one at 320 megahertz. And one lousy asshole radio station can come in and hit that and knock out 5 channels on your TV set, right? And then when you hit these nonlinear transistors here, they beat and they'll make others parasitic signals. And so, yeah, you want to keep it out, but put a good amplifier on the back end so that you get a good signal in and the noise isn't a problem. And you're in somebody's house, so you got 110 volts right there, so power's really not an issue. I mean, as long as you're not being stupid with it, right? As long as it stays small. So now we've talked about twisted pairs and why you use a twisted pair. And I'll point out something that I've seen done a lot, I won't say where, is RS-232 has RX, TX, and ground. And what I have seen people do is tie the ground to a shield and then twist TX and RX together. Now, can you see what the problem with that is? They say, oh, we've got a twisted shielded pair. It's noise immune. It doesn't make any noise. Do you see the problem with that? I send an electron this way. To go over here to this guy, to this amplifier. And now what I've done is I've created this, and I'm trying to pull an electron back this way.
But they're not.
But he's not turned on, and he's not trying to drive one, so what's that going to do? It's going to pull the voltage down. And what's that going to do? Well...
yeah, because it's not electricity. It's not sending an equal number of things back, right?
It's not trying to.
It's not trying to. It's being forced to in this case.
Now, if you're using true RS-232, which has signal levels that are like -5 and +5, and this is an indeterminate zone and doesn't count, and it can go as high as +12 and as low as -12, maybe not such a big deal. But if you're using CMOS, 0 to 5 volt levels, that can be a problem. That can really screw up your signal. People think, I've seen too many people do this. And I sit down and I say that you can't do, I say, you can't do that. And they say, well, we've been doing it for 20 years. I'm like, okay. I understand that you've been doing it, and yes, you can do it, but why do you do? And so we go through this whole discussion I just had with engineers who are older than me and been doing shit. I said, why do you do a twisted pair to get noise down? How does it work? Well, I don't know. And then I end up going through this whole thing with them and saying, this is how a twisted pair works, and what are you doing? You're creating a false signal on your receive every time you transmit. Same on the other end. What you should do, if you want to have the noise immunity, is either just run them side by side and tie that to shield, which is, yeah, okay. But you still got these two wires laying next to each other. What you should do is branch this out
twist them with
and
individual
do two
grounds.
twisted pairs.
So essentially, you end up with a common neutral
Right.
and twist individually with it.
And you should do a number like that. Like that. That's what you should do. And then this is kind of bad, but we won't go there. You need to have that just to tie the references together. That's all it's really for, is to tie the references on both ends together so that 5 volts is here as 5 volts is there. So now we've done twisted pairs. This whole thing is called inductance. And it's these two right-hand rules, this one and this one. Right? Current running that way, and current into the wall. 3-degree, bad 3D drawing. So now some interesting practical applications. This. Now if I have one coil of wire, well, if I do one loop of wire, what I see is right-hand rule, current comes in, all the way around and out, so I'm trying to draw the current. These are magnetic fields, so if current's flowing this way, this side is north, this side is south. Electromagnet. Single loop electromagnet. Now, if I take this one wire and I go around and around and around and around and around and around, and current goes in here, right, so it's going to be rapid this way, which means this field's going to be coming like this, which makes this the north side and this the south side. Because each of these is right next to each other and they're effectively amplifying the guy next to him. And so you get to this equation where you can do some pulling things out. This is current. But the inductance of this is you've got permittivity, or is it mu? It's mu, is the magnetic permittivity of the stuff inside. And again, for air, it's like 1. It's mu and mu naught. And what happens is, if you've got an air coil, this can happen really fast, because there's nothing to resist it. There's an idea of magnetic resistance, if you will. A core of a transformer is metal, because what it does is it focuses that energy and makes sure it goes through right there. So if you see like a toroidal transformer where they've got this metal bar and you've got why is it so hard for me to draw? You've got this thing going like this, right? All of the magnetic field stays inside, it's in the center, but it's expanding and collapsing outside, so it focuses the energy in one place. Keeps it from going out. It brings your coupling factor up. That's this K factor here. This mutual inductance of a transformer is L1 L2 square root times K, which is the mutual. It's a efficiency factor is what it turns into. So we've gone, and this again is your electric motor, right? If I've got a magnet here and a magnet there, if this is a north magnet, it's going to repel this pole, and it's going to attract this pole, so it's going to come down like this, and that's going to go up. So that's a north and that's a south. And I've got a slip ring back here that kind of connects here, and well, we'll do it this way. It connects here and connects there. So this is positive voltage and this is ground. But when it flips to this certain point, then it hits the other one, and now current's flowing the opposite direction through it. So now the poles switch, well, this way. What you're doing in your electric motor is switching your poles back and forth. And you got two permanent magnets that sit there and attract the pole around and keep it going.
Got it out now.
Bye-bye.
Thanks again. Always appreciate it.
Yeah,
I got to catch up on this one. I missed half of it because I was dealing with crisis. So.
that's all right. That's all right.
But thank you very much.
So we talked about electric motors before. This is kind of going back into an electric motor and what an electric motor is. So that's what's going on in an electric motor.
You're creeping off frame.
Am I?
Yeah.
Yeah, I know I'm right near the edge.
Yeah.
So now you start talking about, if you get down into the nasty, I talked about V is equal to the inductance times the change in current twice the change in time. So a capacitor let high frequencies through, but it blocked low frequencies. Inductor does the opposite. It lets low frequencies through, but it doesn't like to let high frequencies through. Because if dt shoots to 0, if I V dt over L equals di, so as the time goes down, higher and higher frequency, the current goes down. And so the curves are exactly the opposite, right? If I do, before I did this, I'm sorry, and that was a low pass filter. That's a low pass filter. And then this is a high pass filter. But this is a high pass filter. For exactly the opposite reasons, right? As high frequencies want to go through, high frequencies don't want to go through. Low frequencies want to go through, low frequencies don't want to go through. Notice their topology is exactly reversed. If you start putting an L and a C together, now you've got a two-pole filter. And the pole is at 1 over 2 pi square root LC, I think.
So,
Which is Q.
so that is a what type of? It's still low pass?
This is a low pass. He'll let a low through. He won't let a high through. And he'll block a high. He'll let a high through. So high frequency goes this way. Low frequency goes that way. But now it's two poles. So instead of like 10 dB per decade, it's 20 dB per decade. Games can be played. Inductor, V equals L di dt. This magnetic field, I mentioned this before, like that electrostatic field in between the two plates of the capacitor, that's square root of -1.
So an inductor is that like the that's a choke. What's I'm thinking about what that looks like in real in like circuit, you know, a piece.
If you're talking a ferrite bead, it looks like a wire in, goes out, comes back in, comes out, maybe goes back in, comes out.
So it sort of does look like it. I mean,
So that's a toroidal.
okay.
That's a regular inductor. That's a toroidal. Who knows what that is? And this is a very good representation of it. I drew the toroidal one here a little bit ago, and it was awful.
I was thinking of those as chokes, but it's an inductor.
A choke is another name for an inductor.
Okay, all right, that's where my...
It chokes off frequencies.
Yes.
It chokes off noise.
Okay.
That's where the name
All right,
comes
we're
from.
talking about the same thing now. That's where I...
A choke and an inductor are the same thing.
Okay.
They are.
Cool.
It's like voltage used to be called tension, right?
Yeah, okay, cool.
We don't teach chokes anymore because that's karate, not electrical engineering. Unless you hate your boss, in which case it can be.
Can't be both.
All right. So, talked about that. So we talked about how this is going to resist the change of current. I used, I didn't do this before, earlier, but I did it however many classes ago. A capacitor can be thought in terms of water. If I put a rubber membrane in a can, I put pressure in, and if I just leave this to air, then this is going to bend this way. It's like a water balloon. But then whenever I open the valve, if I close this valve and open that valve, then it's going to push the water out this way. I'm storing energy in the membrane. Over here, I'm storing it in the electric field. So when you start getting into these square roots of -1 and you start doing math on these things, you start ending up with these equations that are like 5I, blah, you know. We talked about Ohm's law going through a resistor, V equal IR. But as soon as I start going into a capacitor, well, you start seeing that has a frequency dependence. And that frequency dependence, you start talking about phasors, because Eli, the Iceman, voltage leads current in an inductor, and current leads voltage in a capacitor. Because of all these same things, right? He looks like a dead short to high frequency stuff. As soon as that edge comes in, the current goes through. And so you start talking about phase angles. So if my if I do this, I've got a voltage source here, and he's putting out a sine wave. And if I measure it, voltage and current, if I measure, this is a ice voltage here, I'll see current here in time. Current leads to voltage. Because as soon as that voltage starts coming up, it's at a high frequency, this thing looks like a dead short, lets the current flow through. Or actually, if I put that to ground right there, just look at it that way. And if I measure my voltage right here, this is what I'll, and current right here, this is what I'll see. If this is an inductor, the voltage changes, but it doesn't want to let the current change. This is the drawing I made before. If you think of this, a paddle wheel with a flywheel attached. Water flows, spins the wheel, it wants to keep going. When you shut it off, it still will want to keep going. That's an inductor, and it'll pull the voltage down. So if I measure resistor into inductor and the same power supply here, what I'll see is I'll see my voltage do this, and I'll see my current do this. Left to right in time, right? My time axis is this way. Now, from a practical point of view, impractical. So we start talking about phasors and whatever and negative numbers. What we're talking about in these negative numbers is or I'm sorry, these square roots of negative numbers, so 5i, 6i, whatever. What we're talking about is this phase angle, and this is the storage of energy. You're talking about energy. You can't see it, you can't touch it, you can't feel it. It makes your hair stand up because the electrostatic charges and whatever, and it has effects on things around it where it's being transferred, but that's energy stored in a... Whenever you get into these funky equations and you get negative numbers, that's energy somewhere being stored in some... transformed into some other form. You know, because you got to conserve energy, right? It's still there, but now... And now you got phase angle, so when you start talking about power, if you got a big factory with a lot of big electric motors turning can openers and bottle openers and bottle washers, and you look at how it's made, there's all these things going around that you can tell that's an electric motor driving that, that's an electric motor driving that, because that conveyor belt ain't doing that all on its own, right?
We hope not.
What you end up with is you're sucking a whole lot of current, so the generators assume a resistive load. So voltage and current are going to be, I mean, your power supply, your big generator that's coal powered or whatever and generating a 60 hertz sine wave is generating the voltage, and the way it's wound, it's expecting the voltage and the current to go together. When it hits an electric motor, okay, a DC electric motor doesn't matter, but now you get into an AC electric motor, and now you start having these things happen. Then you're pulling current ahead of the voltage, and that's overworking the generator back here. It's actually as if you're pulling more current than you really are. And you talk about a phase angle and a power factor. And a power factor, it's the cosine of the phase angle, if I remember right. So if your power factor is 1, that means you're perfectly in line, and you're using the current as the voltage is being supplied, and not using it as it's being taken away, or giving it up as it's being taken away. Utilities will start charging. They don't charge us residential customers for this, but they might start one of these days, because all these switching power supplies are heavily inductive. They're sucking current left and right, out of phase with the voltage. You know, up until a few years ago, it was lights and shit like that, and they were pretty well much power factor 1. Now we're power factor, let's see, I think when your current leads, it's a negative power factor, and when your current lags, it's a positive. Maybe it's the other way around, I don't remember. Positive power factor is leading current. Positive power, I'm pretty sure that's right. Factories get charged for power factor, and it's called VARs, volt amp reactive. So when you start talking about AC, you're not talking watts anymore, you're talking volt amps. Because at any given time, I might only be drawing 5 watts, but the effect back on the generator is this thing stretched over weird time, and so it becomes volt amps, and it's a square root of 2, or if it's 3-phase, a square root of 3 adder.
So that basically causes an imbalance in the transmission?
Yeah, and it causes heat to be generated in the generator more than, because now at the peak, when I've got that loop of current, that loop of wire that's generating, so if I take that electric motor that I did before and I do exactly the opposite, I spin it really fast, and as it goes through the sine waves and the current starts flipping back and forth, it's going to make AC coming out the backside. And, or it's going to make a pulsating DC come out of it. And this has some resistance, and if I were just to dead short this, right, then whatever current I can push divided by V equals IR, right there it is. And so I can figure out the power being dropped, P equals IV. There's my two major Ohm's laws. I can say there's this much current in this line, but now if I'm off peak and my voltage is down, I equals V over R, or let's do it, P equals IV I squared R, or P equals V squared over R, right? Those are a couple of different equations that we can pull out of that. Now if you imagine that I'm here at my peak voltage, but I'm not at my peak current, my total power goes down that I'm developing. But then when I come off, and this thing's coming out of the page, and I'm off of where I would be generating my peak voltage, which is where I'm perfectly perpendicular to the magnet, then my current's shooting through the roof, because to maintain the V over R, the P equals IV relationship, if V's going down but power's remaining the same, I has to shoot through the roof, which is causing this guy to overheat when he shouldn't be. He's causing him to heat when he shouldn't heat.
Interesting.
Wears them out. And so for industrial customers, power companies charge for power factor. And so for a industrial company,
I'm thinking an industrial company puts something on premise at a certain point to...
yeah. You'll even do it for a regular electric motor. So if I've worked on some designs, I've got a feed here, I've got a 10 kilowatt transformer over here in the corner. Okay? It's actually a 10 kVA transformer. So over here's a 10 kVA transformer, and I come over here and I've got a motor. Well, actually this. And I've got a 10 kilowatt motor. So it's 10 kilowatts of power that I'm going to deliver. It's what I need. That's going to be divided by square root of 2 or square root of 3, depending on 3-phase, 2-phase, and a few other things. That's going to be something like 12 kVA here, equivalent, because of all the shit that we're talking about back here. So that means that my 10, you do this thing, right? A motor is about 0.9 efficiency, about 0.7 power factor at best, maybe 0.8 if it's really good, but 0.7 is a good estimation. So 7 times 9 is 63. That means coming out of here, if I want 10 kilowatts of power, I'm only going to get 0.6 of P in, P out, about equal 0.6 P in. So I'm going to get about 60% overall efficiency through, because of power factor. I mean, I'm getting closer to a good wound motor will give me 90-95% efficiency going through. Most of the losses are mechanical, but and my power efficiency is getting the same, but because I'm at 0.7 power factor, I'm really driving this guy hard. So if I look at, if I want to say I've got 10 kilowatt load here that I really need to drive, 10 kilowatts is about 749 watts to a horsepower. So that's about 12 or 15 horsepower. So if I'm wanting to run that many horsepower over here, I come into this, I do a 0.9 efficiency, so now I'm already at divide by 0.9, so that's like 11 kilowatts. So, you know, the beginner rookie thinks, well, I need an 11 kilowatt transformer. kVA, V times A, P equals IV, watts is equal to amps times volts. If it was a purely resistive load, 11 kilowatts and 11 kVA are the same thing.
Okay.
But it's not a purely resistive load for all the reasons we talked about here. And what's going to happen here is you've got this inductive core that we talked about, and it's going to get hot. It's going to heat up. It's going to do all sorts of crazy crap because of magnetic hysteresis. And so now I need to divide that by a 0.7. So 11 divided by 0.7 is closer to about 15 kVA. So now what I can do is sit down and do the math of L and C. Now I can put a capacitor back here. And now, when he's charging up at his peak, he looks like a short, and he gives me his energy ahead of when he needs it. So he absorbs all this energy, and now he's trying to use it when it's stupid to use it because the voltage has gone lower, but now he can supply the current. And then what I see back here is a power factor that moves back up to 0.95, and now I don't need, now I can go back closer to an 11 kVA transformer because I've done it's called power factor correction right here. Now what you would see happen is if you run motors at idle, it's really weird. Motors are designed for a load and an RPM. And if they're running at that load and that RPM, their power factor is really good. But if they're off of that, if they're like just starting up, their power factor is ass. Or if they're running with very little load, their power factor goes the other way because the inertia of the system tries to work against it. So what you'll see at some factories is they will set up a whole bunch of motors just running, but because they're running with no load, it causes them to pull the power factor forward. And these other motors that are actually doing the load are trying to pull the power factor the other way.
And it balances out.
And it balances out.
And that's probably at a certain, I mean, I guess capacitors at that kind of thing are highly expensive.
Yeah.
So,
but, and a big AC motor's less expensive. It used to be. I don't know about now.
Yeah,
it's less expensive than one of those things. So if you've got these motors sitting here running, you're using more energy overall. But because your power factors come back closer to 1, you're getting charged less overall. So you're wasting energy to get a better power bill. How's that seem backwards, right?
So that extra heat, I'm thinking back to like how that equates back to something that I hadn't thought about and somebody brought up. The power connectors for an AC motor are actually different than the same current for just for a non-motor thing, and I'm assuming that's because of this.
It's not the connectors, but the wire sizing and everything is where it comes down to, and you're looking at. And there's actually inrush currents and start currents because when you first start it up and that thing's
sucking a lot of
when that first what's the word, not crowbarred, it's lock rotor current is if you come along and you just put it, you lock the rotor in place, that's the current it's going to draw, because once that thing gets moving in there, it creates a reverse EMF, electromagnetic force, and the power drawn to once you get up to speed and things are running,
it doesn't take as much.
It actually generates a little bit of reverse power. Any motor is a generator.
Yeah.
So it's actually it's kind of funky the way it works.
Well, I mean, an alternator is, I mean, it's
that's not a permanent magnet. That's got a field coil, but yeah.
Okay.
You can't run an alternator like a motor. You can run a generator like a motor.
Like a motor. Okay. Yeah.
So my old Model A truck, I can turn the generator into a motor. In fact, the starter motor is the generator.
Is the generator.
Yeah.
Nice.
And so if you leave it in gear and tow it down the road and the lights are on, the lights will come on. Even with the battery dead and not in there. So yeah. Power factors are ugly. So first thing we can do, practical use of an inductor, we talked about filters. The second practical thing we can do is called a solenoid, or a relay. So if I've got this coil of wire that I've drawn down here, and I put a metal bar in it, when I turn it on, when current flows, it's going to energize. That magnetic field is going to be coming out this way, right? Like we talked, we're going to have a north and a south. But as it grows out, it's going to cause a lot of time. There's a couple different ways you'll do this. You'll see a spring on them. As current flows one way, it'll tend to push the bar out. And then as it turns off, the spring will suck it back. Or you can run current one way and it'll push it out, and run it the other way and it'll push it out the other direction. So you can make a linear motion, a linear motor out of one of these. They generate a lot of heat. It's not the best way to do it. But they're useful for a lot of things, for small things. Or you can do a relay type thing, an old doorbell. You press the button, and there's the hammer right there, and there's the bells, and there's a spring that pulls it up this way, and it goes clang, and then 60 cycles happens, and it goes clang, and then 60 cycles happens, and it clang, and clang, 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 ding, with this high-pitched tone that's whatever the resonant frequency of those two bells is. A relay is a switch, right? So I can do this. Why the hell would I want to do that? Because if that's a 500 amp switch, that's going to throw a hell of an arc. It's going to blow up and under my finger. But if I can do this for like 2 milliamps and turn on this giant frickin' switch over here that turns on the power to the whole city, it's designed to hold all this power, and it can be controlled by this little thing here, right? So a very low amount of power here can cause big things to happen over here.
For DC versus AC.
Sure, this could be
Separated. Yep.
This could be a 5-volt battery, and this could be 110 volts AC. And it's all isolated then. There's no connection between the two. Yeah. These have a tendency to arc right here and eventually wear out, but
I have replaced a lot of them.
but they're good. You know, they are still used, and there's reasons why you would use those over other things, depending on what you're doing. There are some that are magnetically latching. You can do the circuit such that when it hits, it energizes itself. So you can kick it and just walk away, and it'll stay latched. And then you don't have to keep power going to it. It feeds itself. And then you do a power interrupter to kill the power and make it unlatch. There's some that are magnetic, and when you hit them, they latch, and you have to actually hit them again with the opposite polarity to unlatch them.
Unlatch it.
Yeah, they use those in space. Because you can latch them and walk away from them. No power used. Stays latched.
Oh, yeah, that would make, yeah.
A metal detector. The tuner on a radio, or an older radio, the way the tuner works on an older radio is you've got, well, there's two ways. You've got this big inductor, and you slide a pickup on it, so it looks like could be here, and it changes the inductance going into the tuner coil. The other's with an air gap capacitor that they sweep through, and it changes the capacitance, same effect. This is a metal detector. You can do fun things with this as a metal detector. You put a very small amount of current down here into a coil that's got a gob of coils, comes back up, LDI dt. If this, we talked about this, has a mu factor. So whatever this is actually mu r, which is equal to mu naught times mu relative, just like the epsilon was before. If this is a piece of metal, then you changed your mu. If I take a piece of metal, so I've created this magnetic field that's, say, north and south, and now there's a piece of metal in the ground underneath of it, or in the wand that the guy's passing over you, it changes the L, mu changes, L changes, current did not change, so voltage has to. Bang, I just detected metal. Conductive metals. Usually ferrous. Ferrous metals. Ferrous metals. Aluminums, they can, but a DC won't affect it so much. But the other thing is, too, you get this whole thing, if it's conductive, as it comes across, it makes a change in field, right? Because you're doing a permutation on this field, which is going to permute the current or the voltage. So now you got a metal detector. Or if you go back to the idea of a solenoid, and you put usually a permanent magnet in the middle, and hook it up like that, you got a speaker. Or, let's see, I think I've beaten mu to death, and the inductor to death, and the right-hand rules to death. If I put two inductors side by side,
Transformer.
I have a transformer, because as the magnetic field expands on this one's going to want, so as current goes this way, voltage goes up on my sine wave. As voltage goes up, current's going to go through here because we're staying in phase and power factor is unity. And now on this side, as this comes across, remember our two electrons here trying to go opposite directions, this is going to induce a current this way, so voltage is going to go down, and then as it comes back up, it's going to go up, or when it goes down here. And so this is what these dots represent, is the phase. When this one goes positive, that goes positive. When that goes negative, this goes negative. Those are phase dots.
Okay.
And sometimes you'll see a transformer that's labeled this way, and all they've really done is that. And then there can be center taps, so you can do fun things. Your house, we talked about this a long time ago. Your house is actually fed your house is fed by like 3 kV, I think, like 3,000 volts here, and this is 240 volts, but this is tied to ground, so this is 120, and this is 120. So you effectively get two 120 circuits. So if you've got a 120 breaker, it's going across this one, or it's going across, actually, if you look at them, you got breakers on the left and the right.
They're opposite.
Well, it's a,
If you can draw that the first time I'd be impressed.
This is A, that's B, that's B, that's A, B, A. It's gotta be A. It does a number like this. They come across each other like this. So when you drop in a breaker here, that's a breaker.
Whichever other one.
No, it's B, yeah, it's A, B,
Yeah.
A, B.
Yeah. Because two position gives you both legs and gives you 220.
240.
Or 240.
Right. So a double position breaker is this. And now you got 240 across those two lines. And this one gives a single, and everything comes back on neutral, which is tied to ground right here. That post, which is this right there. So A, B, A, B, A, B, A, B, but I think they're actually, they might be A, B, B, A.
I think it's A on one. It starts as A on one side and B on the other.
Right.
And then, yeah, because they actually go behind each other in the interlacing.
Yeah.
One goes low, one goes high on the back.
And that was what was screwing me up.
Yeah, it's hard to draw. That's why I was like, I don't think you can easily represent
So
that.
if you remember that we go back to inductance is directly related to the number of turns of wire in there. That was back that mu naught n whatever. We find that if you if I have 5 turns here and 5 turns there, then that's going to be 3 kilovolts out there. And if I put this on a load that's 1,000 ohms, for instance, just to keep numbers easy, This will be a 3 amp circuit there, and that'll be a 3 amp circuit there. V primary divided by V secondary is equal to I secondary divided by I primary. Power equals power. IV times IV, power has to be maintained. Minus any losses, right? You're gonna have some losses. But, so now, but we see that V primary and N secondary is equal to Vs and number of turns primary. So Vs is equal to Vp, number of secondary turns, number of primary turns. So if I want this to be a step down, if I want to go from 3,000 volts to 200 volts, well, let's go to 300 volts because that's easier. Then I have to have a 10-to-1 ratio where this is 10 turns and that's 1 turn. So probably more like 1,000 turns and 100 turns. And V primary is 3,000 volts, and now this is 300 volts. But if this is 1,000 ohms, now that's 0.3 amps. But I have to conserve energy, so 0.3 times 3 is 1,000, 3,000. I'm making a mistake here. It should be 1/10. It should be 0.03 amps.
Yeah.
Because power has to be conserved. 3,000 times 0.03 is 300 watts. 300 or 100 watts. 100 watts. 300 times 0.3 is 100 watts.
Okay, so now that's, we refer to a transformer in, I guess, 2 real scenarios. There's staying with the same, saying DC to DC or AC to AC, and then there's, I mean, we still consider it a transformer. Is it really a transformer if it's AC to DC?
Going AC to DC depends.
Okay, all right.
This is something we drew out a long time ago. Got the transformer. Comes to the wall, right? Here's your 3 prongs. Hot, neutral, ground. Over here. This would be an isolated supply because you're not tying the ground back.
Okay.
You're tying to, we'll call this earth. That's what that stands for.
Yep.
You can imagine the 3 makes an E. Here is chassis ground. So now we're talking about different kinds of grounds. Usually earth ground and chassis ground are tied together, like in your house. These are tied together. This will become your neutral. But what you'll do for a DC power supply is you'll tie this to chassis, and this becomes your reference ground also. So, and then out here it comes to earth. So now I've got ground's a ground, the whole world ground. Ground is ground. But these symbols represent that it's a chassis, that it's tied to the outside of the box. So if something shorts out and blows up, it's going to go to ground before it goes to you.
Okay, yep.
Protection. But now I say this is my signal ground. And it could well be, in some cases, that he's not tied up. Chassis is tied up and there's some resistance here. On purpose.
Okay.
So these 2 grounds are the same, but these 2 are not necessarily the same. If there's any current flowing, then they will very suddenly not be the same. But this will still get anchored to ground because this is the same symbol. And this will blow up or do whatever it's going to do. But there are times when you do it this way and there's reasons to do it.
Like why?
Ground loops. You don't want signals here running out and coming out here and polluting things over here, and you get weird, goofy things happen because current always has to get back to where it came from, and if it finds another way to get here, and then it has to go all the way back here, and everything quits working. Ground loops are a pain in the ass to troubleshoot because you don't know. You got to start turning things off. Click. Yeah, that thing's still not working. Okay, we'll turn that back on and come over here and turn this one off. No, it's still not working. Fuck. Now we'll turn both of them off. Oh, okay, now it works. All right. Somehow current's going away and coming back in through these two things and getting noise on it. And
if you lose of a 3-phase, if you lose one, I think it's on a 3-phase. No, it might happen on a 2-phase. If you lose one of the legs, you a lot of things will work until you turn on a motor, and then like strange shit happens. Light bulbs come on that aren't turned on.
I had that happen in my house.
Yeah, a buddy of mine had it happen.
The guy installed the two. I had done the original wiring, and I did 100 amp wiring, and I installed a 100 amp breaker, and you're supposed to derate it by 10% for the house, and I didn't realize that. Guy's bitching it. Who's the idiot who did this? I'm like, well, it was me. Well, the guy who did this is an idiot. Well, okay, that's me. What did I do wrong? It should be a 90 amp breaker. Oh, all right. Because the truth was, I had more than the cable was big enough for that, and whatever. So he, when he put it in, the breaker didn't seat right, and it was this way for a couple of years. And I started getting this weird problem. I'd go up to my daughter's room, and the lights would sit there and flicker. She had the compact fluorescence in there, so they'd just sit there and just kind of flicker, but they'd never come on. But the fan would work. If you turn the fan on, then the lights would really start to do weird shit. And I spent a couple of days, and I was like, I've got a dead leg. But everything else in the house is working, but not these couple of things in her room, and they were on that other phase. And I had my air compressor turned off for whatever, it wasn't running, so it would have
done the same thing.
It would have shit the bed or whatever. But I ended up going through the house, going through different outlets. Oh, yeah, that one's 110. But when I turned so it was a high resistive connection is what it was. And when I pulled the breaker out, it had little arc marks on it. And so I bent everything back into shape and plugged it back in, and everything was fine. And it was weird. I had the longest time troubleshooting this because I troubleshot it for over a year. Because it would, okay, there's something going on. Dad, our lights aren't working. All right, well, I'd flip the breaker, this breaker. They're still not working. All right, come over here, flip they're still not working. I come over here and flip one that was completely unrelated.
And everything.
They're working.
That could make you drink a lot of beer.
Hell then. This is the one to the kitchen. It's got nothing to do with your room that's on this other breaker here. What? Oh, God. And, you just smacked things just right.
And everything worked.
Yeah.
Until you turn on something else.
No, and it worked for a while until, heat and cool, and it loosened up a little bit again. Oh, son of a bitch. And it's not something you can check because it's a blind mate, right? So the guy who came in and did the inspection afterwards was like, yeah, that's in there right. And, yep, the lights work. It must be fine. All right, where were we?
We were talking about converting. We were talking about
right. So you can do a transformer, and then the transformer can go into a half-wave rectifier. So a diode is a special device. If you think in the terms of water, it's a ball valve. Water flows this way, it pushes the ball out, water keeps flowing. Water tries to flow this way, it sucks the ball in.
Yep.
Water doesn't flow. A diode's a ball valve for electricity. It's a semiconductor ball valve.
You've used lots of them.
What's that?
I've used lots of them.
There's also a diode tube, a neon rectifier tube. does something similar. A neon tube only conducts one direction. That's why you can see them flicker.
Interesting.
So current voltage is doing this. I've got some load out here. I'm keeping everything resistive to keep numbers, keep life easy. And now what I get is this. We talked about this when things go bad. Now I put a big ass capacitor here, and it does this. And the bigger this big ass capacitor is, the flatter this becomes. And there's a ripple spec for that. Then the next thing you do is you say, well, this sucks, I'm wasting all this time, and I have to have these giant freaking capacitors here. So you very rapidly get to a full wave bridge. No. Well, yeah. If he's positive, flows here. Let me do this to make it really clear. So positive, if he goes positive, it's blocked. If he goes positive, it passes through, comes out this way. It's this way. If he's positive, goes through, goes that way, comes in, comes this way. If he's negative, which would mean he's positive, because these two halves are out of phase. Positive comes through, comes this way, comes back in, negative this way. Now I call this my ground. And when I look at my load, I see this. The 60 hertz, 120 hertz. Doing current steering. And now I need much less capacitance than I needed before because I don't have to fill up this gap, now I only have to fill up that gap. Same amount of capacitance gives me a better ripple spec on the output. Using the transformer as an actual transformer. Now, this M, this is a K is a coupling factor. It's the mutual inductance. If I look at this, this looks like an inductor going through. And you can actually play impedance matching games with a transformer. That's why there's impedance matching transformers on audio circuits. Because your mics are usually really high impedance, but what you eventually get to is an 8 ohm impedance out on the speaker. And you got to do some transforms in there. And transformers are a good way to do that. They transform impedance too, not just voltage. But this K factor is also, this coupling factor is also part of the efficiency. That's usually higher than 0.99 on a good transformer.
Okay.
So you usually don't notice it, but once you get down to a 0.96 or 0.95, you're losing energy going across this gap, and then it's really fast drop off. So we'll kill that. The next thing that we're using inductors for a lot is power supplies. So I can do two things. I can do this thing up front, so I've got some DC level coming in, and I've got a controller here, and I've got some DC A and DC B coming out. And I've got ground. Now, there's if DCB less than DCA, step down, buck converter. I can do this. I won't draw all that. That's TMI. V-sense. Right? So I sense my output voltage, and I've got some oscillator that drives this thing. It's probably driven off of this voltage or something, and there's some reference it's all inside this box. There's a reference that I'm comparing to and whatever else, so I know what this is. We can talk
What's
about
actually happening.
I know what
beat
this
side.
really. I know what this really is, and it's because of a couple of different things that I can do, and we won't talk about tonight because now it's semiconductors and diodes and other stuff. But this thing controls this switch. So now if I look out here at my load, let's say this is 12 volts and this is 5 volts. I close this switch, current flows. Voltage is too low, voltage is too low, voltage is too low. Voltage is 5 volts, I open this up. And I need another switch here, I'm sorry. Dang. These work opposite of each other. So this is open, this is closed. So this inductor wants to keep current moving, right? So I open this switch, I close this switch. 4 volts, 4.5 volts, 4 3/4 volts, 5 volts. Close him. Inductor wants to keep that current flowing, right? So now current does this. It's doing this. 5 volts, 4.99 volts, 4.98 volts, 4.99 volts. And what you see out here is if you measure your voltage, you see it's a sawtooth. Or it saws this way. But usually what they'll do is it's smarter than that. It pulse, 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 and it'll keep pulsing, but it'll change the pulse widths and do a PWM on this to keep it sunk up. That's a buck. And now, you throw a capacitor in here too, and now you start smoothing that out. That's how a buck converter works. I'm playing a game with a switch and an inductor. Now, boost converter.
It's past 10, just to let you know, bud.
All right, we're going to be done here. We're going to talk about a boost converter. If DCB is greater than DCA, then it's a step up and it's a boost. Topology. I got to think this one through for a second. So now I've got 5 volts, and I want 12 volts. And oh yeah, there we go. Something like this. something like this. Again, these switches are reversed. Now, these you got to be careful with because they need minimum loads. You got to be careful with these smart ones that they don't. Some of them don't like to have no load. If you have no load, they break. Things go wonky. Can. Not necessarily will. Depends on how they're made. And you can see why when you start seeing the game we're playing here. Current flows straight to ground. I open it up and current comes in and I let it go to ground and then I close this one and open that one. He wants to keep current moving. I had a lot of current going in there, right? I mean, this was basically a short to ground. So now I've got 5 amps going in and I've got 3 ohms. So, sorry. Yeah, got 4 amps going in. 4 amps going in. And now I open this up and I close that and I got 4 amps going that way. 4 times 3 is 12 volts. Now I've got 12 volts out here. And now as this current decays, the voltage starts to come down and I say, oh, shit. Now I got to close this one and open that one. And now I get this back up to 4 amps. Actually a little more than 4 amps, right? Because you want to play above where you need to work. And then you do it again and you keep it. And so what you see out here, if I don't put a capacitor there, is I see a voltage that like comes up and then drops, depending on what you have out here, drops away and does this. So I get this weird peaky thing like this, where this is maybe 13 volts and this is 0. Looks a lot like that, right? Now I put a big ass capacitor here and that smooths that all out. And I start ending up with something that looks like that.
And what's our amp drop is?
So you got to conserve energy, right? So if I'm doing 4 amps here, but it's at
You can't do 4 amps there if you went from 5 to 12 volts, can you?
I did. That's how I did it. But what I see is that to be able to do that on this side, it has to convert, and you have to maintain, you have to conserve energy. So 12 times 3 is P equals IV. IV is 4 times 13 is 52 watts. That means I have to have 52 watts on this side. Divide V equals P equals IV. Divide by 5, that's 10 amps over here.
Yeah, okay, well what I was saying was you have 4 amps written there. You can't, yeah. That's what I was getting at. You can't have 4 amps on that side and have 4 amps over there and step up voltage.
And then there's some, and then both of these things have some losses there. So the minimum efficiency hit, you're never going to get 100 right off the bat because that thing's sitting there soaking some current, doing some stuff.
Yeah.
But now you're playing this game. And I think often there's a inductor here too to help smooth that out. And then what you're doing is you're playing a game here with the mutual inductance of the, well, it's not the mutual inductance, but you have to match these inductors. And so you get right where you're talking, right? You got 10 amps at 5 volts. That means this is L1 and this is L2, and there's a ratio of number of turns there and inductance from one to the other. Otherwise, what will happen is you'll saturate your core and it'll go nonlinear, and then it won't do what you want it to do. So these things are very, you get a lot of these things, they can be very particular. They want a minimum amount of current and there's a maximum amount of current, which you expect, but what happens is if you go above the maximum amount of currents, then you start hitting the magnetic hysteresis of the core and weird shit starts to happen. It can't switch as fast as, you're putting so much current in that you're overloading the core and going into magnetic, basically a magnetic overload is what it amounts to. And what happens is the magnetic hysteresis looks like this. And as long as you're staying like in this area, it's not a problem. You kind of come up and you switch back and you switch back and you switch back. But when you get up into here, you're overdriving it, you come out, and then there's this relaxation time before you can come back. And now your signal becomes all choppy and weird. Now you can do the same thing with AC. And now some of your fancy power supplies that you see these days, this is AC straight off the wall. And now it's all buck converters, right? Because you don't need to go more than 120 volts usually. Usually you want 12 volts and 10 volts and whatever. So this becomes the buck topology. And you might put a transformer there to isolate the two so you don't have AC going straight in your shit. Because then if something bad happens, then it's really bad.
It's bad. Yeah.
It doesn't just go bad, it goes really bad.
You're not replacing a few things.
Right. Right. And now what you see, you start looking at power supplies that you're buying for your PC. These smart switching power supply 800 watts with PFC, power factor correction. It's electronic power factor correction because you're putting all these things in that are electronic, and the switching all looks inductive because you're hitting inductors and you're powering things on and hard and on and off. And the utilities looking at all these people's houses and they're saying, Jesus H. Christ, they're killing us with all this modern stuff. It's playing hell with our generators because it's causing them to overheat. And pretty soon we're going to start charging you morons for your power factor on your house too. And then you'll be then we'll be happy because we're going to be getting the money recouped to replace our generators.
Well, and has that corrected itself based on trying to be, energy efficient? In that, in order to make it energy efficient, you sort of have to to fix that.
It's a little both. I think they play games. I think the power factor correction actually simulates a sine wave on the output. It tries to do a loading that looks like a resistive load. So it does things to
Play with it.
I'm done.
Thank you.
3 hours and 10 minutes.
That was pretty deep.
It was deeper than we usually need to go.